Let's say we have the function y of t equals 350 minus 4.9 t squared, and that this function represents the height, y, of an object dropped from a height of 350 meters and accelerating under the acceleration of gravity, which is negative 9.8 meters per second squared. This does, in fact, give us a model of that fall. Again, it's not a real good model unless you happen to drop this thing in a vacuum. If you got a vacuum tube 350 meters long and set it upright, I guess you could actually get this function. Otherwise, air resistance does play a part, and it doesn't quite work. But this is an ideal situation. This is ideally what your y of t would be if there was no air resistance. Now, we're asked to find the velocity function and the acceleration function, and also the time at which the object hits the ground. Well, the velocity function is the rate of change of the position function, just the derivative of the position function, as you should know by now. So that the velocity is your y prime of t, and the derivative of this is real easy to take. We get negative 9.8 t. I'm not going to go through the details of that. Acceleration is the rate at which velocity changes. So the acceleration function is the derivative of the velocity function. Of course, since the velocity function is a derivative of the position function, that's also the second derivative of the position function. So the acceleration is a derivative of velocity, second derivative of position. In any case, if you take the derivative of the velocity function, you get negative 9.8. Question of when the object hits. Well, it hits when its height is 0, because y of t measures the height above the ground. I think I said that before. That's the condition. Then, obviously, when y prime equals 0, at the instant y prime first equals 0, the object hits the ground. So if we let y prime equal 0, if we let y of t, it's not when y prime is 0, it's when y is 0. If we let y of t equal 0, we get this equation, 0 equals 350 minus 4.9 t squared, and it's very straightforward to solve this for t. We get t equals 8.4. Presumably 8.4 seconds. The velocity at that instant can be obtained just by putting 8.4 back into this equation for the velocity, the formula for the velocity, and we get negative 82 meters per second roughly. And that's really trucking. That's moving 180 miles an hour, thereabouts. It's moving fast. Another problem asked us to determine the derivative of the velocity, or of the volume function for a sphere with respect to radius. Now the volume is 4/3 pi r cubed. You should know that. I find that a lot of people who should know that don't, but that's kind of fundamental. How can you judge a sphere that's thrown at you if you can't calculate its volume before you have to catch it? In any case. If we take the derivative of this function with respect to r, that's very easy. We get 4 pi r squared, and you should recognize that as the surface area of a sphere. Now, how do we interpret this dv dr? Well, it's the limiting value of velocity, of volume change, divided by the change in radius. The number of cubic meters of volume change you have per meter of radius change. And it's the rate at which volume changes with respect to radius. So at a given radius r, this is how fast your volume is changing with respect to r. The number of volume units per radius unit. We can visualize that. Imagine we have a sphere initially of radius r, the inner sphere here, and we expand it by delta r to a larger sphere. Then your delta v is the change in volume of the sphere, and we can visualize that as the shell between the first sphere and the second sphere. Whatever the volume of that shell is going to be the delta v. And of course we divide that by the delta r. Again, we call that the volume change per unit of rate change. It's not rate, it's radius. So change that t to a d, get rid of that.